Hello friends, we are discussing structure, property, processing, correlation in metallurgy and materials engineering. This is very basic lecture and everybody who is interested in metallurgy and materials engineering can attend it, and this will be useful to them to understand the various aspects of metallurgy and materials engineering. These are contents. So there will be basic definitions and classification of materials and historical perspectives of materials. Then what is the materials tetrahedron, that is structure, property, processing and performance. And then we'll be studying structure at various levels, starting from atomic structure, atomic bonding, crystalline structure, chemical bonds, energy bonds, crystalline structure, then closed pack structure, then defects in crystal, then importance of crystals, crystalline defects. Then we'll be studying overview of properties, Ashby charts, processing, how the processing decides the structure. And finally, we will be discussing the example of structure, property, processing and performance correlation. So basic definition, material science. What is material science? So material science involves investigating the relationship that exists between structure and properties of the materials. And what is materials engineering? Basically, whatever we have understood from the material science, so making use of that for designing or using engineering that materials to design different structures. So these are the terms, so material science and materials engineering. Nowadays, most of the graduates in materials program, maybe metallurgy, maybe materials science, maybe materials engineering, those are trained to be in both material scientist as well as materials engineer. Means they will be synthesizing the materials as well as they will be using the material property, structure, correlations for different applications. So what is metallurgy or what is metallurgical engineering? So metallurgy is an art and science of extracting metals from their ores and modifying metals for the use. So this is the very basic definition. And why it is art? So first word is art, because human has started using metals without knowing science behind it. And later, human, during the industrial revolution and scientific progress, human understood various scientific aspects of metallurgy and materials engineering. That's why it is an arts and science of extracting metals from their ores and modifying the metals for the use. So basically there are three branches of metallurgy. First is extractive metallurgy or process metallurgy. So it is related to the extraction of metals from their ores and refining of the metal. So it also deals with the reaction of metals with slags and gases. So basically various steel plants, those people are related to those are to be called to work in a extractive or process metallurgy. And what is a physical metallurgy? So physical metallurgy is again understanding the physical and mechanical properties of metals, how we can vary those by alloying and so heat treatment and how they corrode. So all these things are basically covered in a physical metallurgy as a subject. or a branch of metallurgy. And what is a mechanical metallurgy? So mechanical metallurgy means word mechanical means some force, maybe rolling, forging, extrusion, spinning, dip drawing, stamping, means some forces, how they are going to act on a material and what is its response, means basically shaping related technologies and mechanical testing, maybe tensile, hardness, fatigue, creep, all these properties basically measurement of these properties and again relation between these properties and engineering design. So that is the area of mechanical metallurgy, means from after steel making. I'm giving an example of steel basically, since it is the one of the most used the material. So after steel making, various shaping technologies are there. Those will come under this mechanical metallurgy, and again casting also we can take under the mechanical metallurgy. So we know the classification of materials. There are different classes. So metals, this is the first category, and then plastics or polymers. This is the second category, and ceramics and other basically glasses can come under the third category. And fourth category is a new category, that is a composite materials. So in metals, there are basically two distinct say classification of ferrous and non-ferrous. So ferrous is basically iron base, and non-ferrous means whatever metals, and those comes under maybe aluminum, copper, titanium base. These can be non-ferrous metals. And plastics are again divided into thermoplastics, thermosites, or elastomers. So thermoplastic, as name suggests, we can heat multiple heat and cool them to shape. Thermosite, once they are softened or once they are heated, they will say become plastic, and after cooling, they will not again become a soft under the application of heat. And elastomers, basically they are having elastic property like rubber, silicones, polyurethanes. So plastic or polymer, more specifically, this is a second category. And ceramics are oxides, nitrides, carbides, glasses, glass ceramics, graphite, diamonds. A lot of materials comes under the ceramics. And composites are basically any of the two category, like a metal plastic or plastic ceramic or ceramic, any of the composition, or even we can have different say forms, like carbon can make a composite with a graphite, or carbon fiber can make a composite with some carbon based resin, something like that. So everybody knows these classifications. We can see metals, ceramics, polymers, composites. So this classification is a conventional classification. Conventional means basically this is the very raw classification. Raw means this classification is basically based on the properties of materials. Okay, like metals. Metals are having high tensile strength, less compressive strength. They can be deformed into shape. So ceramic, they cannot be deformed into these shapes. And unlike metals, ceramics are brittle. They cannot be ductile, they cannot be say shaped like a rolling, but they are good in compressive state strength. And ceramics are basically porous materials. They are having high melting point. Metals are also having high melting point. Metals are having a metallic bond. We'll be studying this under the types of bonds. And ceramics are can have covalent or ionic bond. So metals mostly crystalline materials. Ceramics can be crystalline as well as amorphous. Then metals are good conductor of electricity and heat. Ceramics are having varying heat and thermal conductivity. Basically, means very low. So roughly, we can say these are the insulators of electricity and heat. And then polymers, if we compare about the mechanical properties, they are having a less tensile and compressive strength. These are inert to chemicals. So this is one of the specialty. Means metals can corrode under the chemical attack. So we cannot, for these corrosive liquids, we can use polymers or rubbers. Then they are having low melting point. They can be molded into shapes. And these are mostly amorphous. So some percentage of crystallinity can develop in polymers, and these are the insulators of electricity and heat. So basically, their specialty is inert to chemicals and insulators of electricity and heat. So we can have a lot of applications. So before say 90s or during the 80s, you can see all medicine bottles were made up of glass, and even the milk suppliers used to supply milk in glass. After the say industrialization of polymers, we can see nowadays since these are inert to food and chemicals, so means uh, they are widely used in food packaging as well as some tanks. So polymers have a different specialty, and composite basically you can see this diagram in the right corner. So the metals and ceramics, they can combine, they can make some composite, and then polymers and metal, they can make a composite. So in case of a composite, means why there is a need of making a composite. Sometimes if we want to have a high tensile strength, so we can take any metal, we can get a good tensile strength, but simultaneously if we want to have a high compressive strength, then you cannot get a good compressive strength in case of metal. So if we combine these two, means metals and ceramics, so we can get a material which can be a high in tensile as well as high in a compressive strength. So like this, so these are basically made for uh, getting a combination of properties. Those cannot be shown by any of the class like metals or ceramic or polymer alone. Okay, so these are having high specific properties. So basically some of the materials like fibers, these are have a defect-free structure. So fibers, all fibers, carbon fibers, aramid fibers, then glass fibers. So they are bonded by chemical bond only, whatever chemical bond is there in. And whatever defects we are going to study in next slides. So these are defects free. So that's why their inherent strength is very good. Like you can say steels are having say their tensile strength in say 600, 500 or some 1000, 1200 MPa, and more strength of steel are being used. But you can compare whether take any example of fiber like a Panex 35. Panex 35 is a carbon fiber, so which is having tensile strength 3500 MPa. So this much tensile strength we cannot get in a metal. So if we use a proper say bonding material or proper matrix, so we can have these kind of strength at a very less density. So and they are having say good specific properties. So specific, what are the specific properties? Specific property means basically any property divided by its density. So suppose a strength is there. So if you want to calculate a specific strength of a material, strength means roughly most of the time we consider as a tensile strength. So so specific strength of a material can be tensile strength of material divided by its density. So basically these are giving very good properties. Composites are giving very good properties at a lighter weight or at a less density. So basically that's why composites are being used in aerospace applications. There is another classification of engineering materials like functional classification. So functional classification is whatever is the use you can. So this is not a rigid kind of. Suppose here we are seeing 1, 2, 3, 4, 5, 6, 7, 8 classes. So it is not a fix. We can generate as many as classes depending upon the application. So like aerospace, carbon-carbon composite, SiO2, amorphous silicon, aluminum alloy, super alloy, ZDure. And in case of a biomedical applications, so biomedical applications will have a requirement of biocompatibility with say human body, so they should be lightweight. So naturally the candidate materials can be a titanium, stainless steel, shape memory alloy, plastic, PZT. And then electronic materials like silicon, gallium, germanium, barium, titanium oxide. So these comes under electronic materials. So then energy technology like EO2, NICD, ZRO2. So these are related to energy technology and environment. Then magnetic materials, optical materials, smart materials, structural materials. So we are knowing. So there is a vast say application of materials, and we can make as many as classes. So metallurgy means is not a metallurgy, means traditional metallurgy like steel making, iron making, or some non-ferrous metals, casting, rolling, forging. It is not. Nowadays every field of application is requiring different materials. Like nowadays mobile technology or these computers, they require a lot of materials. Even the touchpads, mobile touchpads are having liquid crystal displays. So these are having certain materials. So these are some polymeric materials which are having some crystalline structures. And nowadays you can see very big say research is going in these materials like solar materials. In case of magnetic materials, means nowadays these companies like Intel and these chip making company, those are making computer chips. They are basically trying to write on the smallest dimensions. So they are trying to write on atomic level. So data writing nowadays, we are having more data storage in a small space. So that is basically related to the functional classification of the materials. So, so this now we will understand how these metals or materials are linked with human life. So I this is my personal opinion. So human history or history of civilization of human. So he is linked with the use of materials. So you can say there are different civilization named by the materials they use, like a Stone Age, 2.5 million BC, Bronze Age, 3,500 before Christ, Iron Age is 1,000 before Christ. So you can see humans started making use of stone tools or so whatever utensils. Then the first metal human might have used is a bronze, some casting, and then they later understand metallurgy of copper and later iron metallurgy. So these are the materials, and as human learn more and more related to the materials, so his life has become more and more comfortable. So we cannot think today's human life without engineering materials. So this is the thing I wanted to explain. So this is a materials engineering approach. So henceafter, people are not using the terms of metallurgy, because metallurgy education, I told you, it is not only limited to the steels, non-ferrous and foundry, but there is a learning related to other materials also. So what is the materials engineering approach? So this is you can see in the diagram, this is the materials engineering tetrahedron. So tetrahedron, so there are 1, 2, 3, 4 aspects are there. So first is a structure, then properties, processing and performance. Okay, so we'll study, so we'll understand one by one. So what is the structure? So structure is basically arrangement of internal components. So suppose anything, if you want to define that, so what is the structure of classroom? So I generally give this example. So classroom can be a blackboard or whiteboard, or faculty means a teacher and students, then tables, then chairs for students. So something like that. So all these things basically defines the structure of a classroom. So if at atomic level, so structure encompasses the protons, neutrons, how many number of protons, how many number of neutrons, and then electrons, how they are arranged in different shells. So that can be an atomic structure. Okay. So structure is a very big scale, from atomic to say millimeter level. And then second is a property. So what is a property? Property is a material trait. So it is a basically suppose steel is or metal is there, so we can say metals are ductile. Okay, so ductility is a property. So what it means? It means if we apply external force, metal can be shaped. Okay. So what is a magnitude? What is a stimulus? Stimulus is an external force. And what is its response? Response is it can be deformed into different shape. So it is a trait, means each material is designed its own characteristic or its own trait. So some materials they deform easily. Some cast materials like cast iron, they will not deform that much easily like mild steel. So this is a property. Property of cast iron you can say is a brittle, and property of mild steel you can say means compared to within a metals. Within a metals we can say mild steel is ductile, more ductile than the cast iron, and cast iron is a brittle. We can say if we are considering only the metals as a reference point. Okay. So these materials are having different properties: mechanical, electrical, thermal, magnetic, optical, deteriorative. And in addition to structural properties, two other more aspects are important. One is the processing. Processing is the manufacturing process, how that material has been made, how it has been manufactured. And performance is basically final output, what we want to have. So this is a materials tetrahedron. So while say working on materials, we have to understand all these things are linked. Okay, so this is the objective of this today's lecture or talk. I am want to give the importance how these things are related and why this approach is very important. Okay. So we know structure is an internal arrangement. So how to study structure? So for that answer is a characterization. So characterization is a general term. Basically, it is the process by which materials, structure and properties are probed or measured. Okay. So basically, like a stethoscope, doctor is probing our chest. So this characterization is a technique. These are different techniques. Basically, we are probing the materials to understand its structure and some of the properties. So it is a fundamental process in the fields of material science. Without no scientific understanding of engineering materials could be ascertained. So there are various characterization techniques. Optical light microscopy, it is also called as OM or LM in short, and then X-ray diffraction, scanning electron microscope, SEM, transmission electron microscope. These are some of the characterization techniques. And what is the difference between testing and characterization? So testing is something you are going and say taking your standing on the weighing balance and seeing your weight. So that is a testing. And if you are going for say some bone X-ray, so that X-ray is a different. So that X-ray radiation, okay, what your X-ray diffraction is different thing. It is just like a light diffraction. So anyway, if you want to find out a fault in your bone, so you will be doing X-ray. So that technician will give the output, and is nowadays they are giving a soft copy, so you can see on the photograph. So you will not understand. So there is always need to uh, ex, uh, to have an expert to analyzing the results. Okay, so this is the difference between testing and characterization. Characterization, there is the result is not given as output or on the dial of on that testing equipment. So characterization, in case of testing equipment, it will give a result, whatever you want to measure. In case of a characterization, you need to have an expert metallurgist or materials engineer to understand that. So that is a characterization. So this is, you can see the diagram of right side. So it is indicating the various microscopic techniques and different scales. So you can see the crystal structure is the on the atomic scale, say from 0 to say some nanometers. Then there will be some microstructures which is having dimensions in microns. And then we can study the fractures and so this is in millimeters. So this is the macro structure, and then finally is the compound. So from the components we can study the pores, glasses, maybe a low magnification or naked eye. We can study then optical microscope, then XRD, uh, EM, SEM. So these are this is how we are analyzing the structure at different levels of dimension. So this slide is basically explaining us how structure can change the properties. So all these three discs are made up of aluminum oxide. Okay, but one is transparent, fully transparent. This is somewhat partly transparent, or we can say partly transparent, partly opaque, and this is 100% opaque. Okay, so here from say transparent to opaque. So here the structure will be different. Here structure will be so. This will be having more glassy structure, and some of the basically crystallinity will be going to increase, and when it is a fully crystalline structure, then it can be 100% opaque. So this we have seen from the earlier slide. So atomic structure is in angstrom, and short atomic arrangement, nanoscale, then microscale, and macroscale. So difference in the optical properties are consequences in different in the structure, so which have resulted from the way the material has been processed. So how this structure, we are getting, so we can change the structure by changing the manufacturing process. Some process can be casting. We can either slowly heat, slowly cool. So these are the variations we can. There are a lot of different things, and lot of terms are there. So roughly, and you can understand this. So if we change the processing, structure is going to change, and if the structure is going to change, the properties are going to change, and if the properties are going to change, the performance is going. So what is the performance? Performance is what is the ultimate. Here, transparency, we can say, is a performance in case of this aluminum oxide disc. So structure, again, we are going from the very smaller scale of magnification or smaller scale of dimension. So structure can be divided into solid, means on the basis of states. So we can have different states of materials: solid, liquid, gas, and plasma. So solids are having a perfect arrangement of they are these atoms are held firmly at a place. They can vibrate to their mean position, but they cannot leave their position. So this kind of thing arrangement is called as a solid. And in case of liquid, they atoms or molecules can easily flow around one another, and they cannot go far away from each other. So due to the force of attraction. So means the liquid can take a shape of a container. And in case of gas, means these atoms and the molecules can fly from each other in all directions. So the distance between them doesn't matter. Means, so attractive forces them are insignificant. Means there will not be attractive forces. And the fourth is advanced thing, that is a plasma. So plasma is a state where whole means atomic structure has been broken now. Means you can see positive charges, negative charges, protons. Means everything has been broken out. So this plasma is something which can be means nowadays we are generating artificial plasma in some heat treatment plasma nitriding and all that in case of a metallurgy or metals. But naturally, plasma is exists at star's temperature. So means everything has been at a very high temperature, basically. So and so this is that's why it is shown in increasing energy. So if we give energy to the solid, it can become a liquid, and further giving energy, it can become a gases, and further giving energy, whole atomic structure will broke and make go in a plasma state. So why I am basically why I am teaching all these things from the basic, because we have understood whatever in case of a chemistry, in case of a physics, maybe in 8th class, 7th class, or 10th class, maybe 11th class, 12th class. So there is always a purpose, and there is always a link, and those are going to required those things, or those concepts are always linked with each other. That's why I'm revising all these things. Otherwise, we need not to learn all this. So like we know all these states, but we don't know what is the link with these, with the crystallinity, amorphous. We don't know what is quasi-crystalline, what are the quasi-crystalline structures in nature. Okay, so this lecture or this talk is a very important talk. Means whoever is interested to work in a metallurgy, if he understood this talk, I mean, there are a lot of things I have brought together, and basically tried to establish a whole linkage. Okay, so coming back to our topic, so solids can have a crystalline structure and amorphous. So crystalline is ordered structure, so you can have a unit cell, cubic, FCC, BCC, whatever, and that unit cell or that arrangement is repeated. Okay, in case of amorphous, and there will be some bond length, there will be bond energy. In case of amorphous, there will not be a perfect structure, or so it will not be ordered structure, it will not be repeating structure. So haphazard way arrangement is called as amorphous. Okay, and there is an in-between structure like a quasi-crystalline. There will be a short range order. Means you can see the quasi-crystalline structures. You can have, see circles are here again. There are pentagon, there are say circles, there are squares. So at a local level, we can see some of the order, some of the arrangement is ordered, but on a large scale, it is not ordered. So that thing is called as a quasi-crystalline structure. Solids are so solids are having these three types of arrangements, and liquids are mostly amorphous. Whatever we are roughly say it is a crystal means. Liquids are mostly amorphous, means disordered. In case of polymers, these polymers are also called to be super cooled liquid. Okay, because those are amorphous. But nowadays, in case of polymers also, there is some percentage of crystallinity people are trying to develop. Okay, and there is a clear crystallinity we can have. So liquids are mostly amorphous, and in case of liquid, if short range order is exist, so we can have a quasi-crystalline liquids, and liquid crystals are also there. Myself, I have worked on a liquid crystals in case of a coal tar pitch. So in case of polymeric materials, or in case of some liquids may develop liquid crystals, and that liquid crystal display also, that is another example. So mobile touch screens and that TV screens, LCD, basically liquid crystal displays. So we can have those kind of structures. And gas and plasma, we cannot classify them on the basis of crystalline, whether it is crystalline or amorphous, because there will not be ordered structure. The next level, we can we have started our journey from say atomic to then state, and now chemical bond. So chemical bond is means two atoms, means there are four basically types of bonds, like these three are primary bonds, and secondary van der Waals bonds, you can say, is the fourth category, or you can say these are the three primary chemical bonds, and these are the secondary bonds. Anything, any type explanation you can have. So in case of metallic bond, so metals are having most of the time one or two or three atoms, three electrons in their valence electron shell, and so they cannot either share, or they cannot either donate or accept the electrons like other two bonding mechanisms, like covalent bond. There is always sharing. In case of ionic bond, there is one is donor, one is acceptor. So one become a cation, other becomes anion. So there will be electrostatic force of attraction. And here the electrons, outermost electrons, are shared by two bonding say atoms. So this is a rigid. Okay. So this is not a rigid. So, but still there should be some force of attraction. That's why the bond will takes. So bond is a chemical bond is basically force of attraction is balanced by force of repulsion. That is another thing. You can read how the bond is exist, and what is the bond length, where both forces are matched or equal. Okay. So in case of a metallic bond, virtually these atoms are losing their valence electron. So what will become? So they will become virtually becomes ions, positive ions or cations. And these electrons, they cannot go very far away, but they are exchanging, or they are just traveling inside it. So the resultant structure is a positive ion. So these are fixed, but electrons can pass. So This can be taken as a liquid, or the positive ion cores dipped in an electron sea. So the summation of positive charges and summation of negative charges. So the force of attraction between those is a metallic bond. So that's why it is a flexible, and this is the beauty of metallic bonds. That's why we can have different properties in a metal. Those cannot be available in other types of materials. So this is related to metallic bond. And covalent bond, it is a fix. That's why most of the times we cannot deform them, and their bond energy is very high, melting points are high. Ionic bond is one is a positive, another is negative. So this is the specialty. And the polymers, polymers name, as name suggests, so there is a one formula that is a monomer, and that is repeated to make a chain. So there will be a primary hydrogen bond that is making a polymer. So and there are secondary van der Waals forces. So depending upon these bonds, we can say again classify materials like metallic, say materials, or covalently bonded materials, ionically bonded materials, and polymerically bonded materials. So I told you earlier, this means ceramics can either have a covalent bond or ionic bond. Metals come under this metallic, and polymers comes here. Okay, so metals, ceramics, and polymers. So this table is basically bonding type and bond energy and melting temperature, you can see. So see, C is a diamond here. Diamond is having 3,500 temperature. So then we can review the structure, means how the structure is important, how it is changing its property. So all chemical elements are made up of three entities. One is proton, another is neutron, and third is electron. Okay. And all these particles are having equal weight and size, whatever. Means proton of hydrogen will be equal to proton of helium, likewise neutron and electron. So only the number. Okay, so this is the hydrogen. So one atom, one neutron, one proton, one electron is basically hydrogen. And if there are two electron, two neutron, two proton, so that becomes a different element. Okay. See, the atomic structure change, all the elements will change. So that's why atomic structure is important. Okay. Then there is another say explanation of there is atomic structure, that is energy band structure. So energy band structure is basically having three bands. One is a conduction band, another is a valence band, and there is a field band. Okay. And the band gap between valence band and conduction band is basically making material insulator, semiconductor, and conductor. So if the band gap is very high, then these valence electrons cannot jump easily to the conduction band, and they cannot available for the electrical or thermal conduction. So here, in case of a semiconductor material, so there is say less gap is there, or some other material which will have overlapping that valence band will be there. So that doping is there. Done conductors can be say basically make a conductor. And last is a in case of conductor like a metal, so the valence band and conduction bands are matched, or they are overlapped. Okay. So